In this lesson, we will describe and write equations for the primary types of radioactive decay. When we balance nuclear equations, we look at the atomic and mass numbers. For example, the mass number for uranium in this reaction is 235. When we look at the product side of our equation, we have 231 plus 4 equal to 235. For the atomic number, we have 92 on the left side and 90 plus 2 equal 92 on the right side. Therefore, this would be a balanced nuclear reaction. Notice in a nuclear reaction, we see that the identity of the substances can change. This is in contrast to chemical reactions where the identity of the elements must remain the same from the left to the right side of the reaction. Let's see how to identify the missing particle in this reaction. On the left side we have 42, and on the right we have 0 plus our unknown particle. So we can write this as 42 equals 0 plus x. Solving for x, we get 42. So we know this will be the mass number in our missing particle. For the atomic number, we have 19 equals minus 1 plus x, and the x represents the atomic number of our unknown particle. We add 1 to both sides, and we get 20 equals x. So that becomes the atomic number for our unknown particle. The atomic number represents the number of protons, and when we look on the periodic table, we see the element that has 20 protons is calcium, so we can fill that in for our unknown particle. Now we want to fill in the missing radioisotope. In this case, our unknown particle is on the left, but we still take the same approach to solving the problem. We have our unknown x plus 1, which is equal to 142 plus 91 plus 3 times 1. Notice there are 3 neutrons, so we have to multiply 3 times the mass number of the neutron. We then get x plus 1 is equal to 236. Subtracting 1 from both sides, we get x equals 235. 235 is the mass number of our missing particle. We take the same approach for our atomic number. X plus 0 equals 56 plus 36 plus 3 times 0, and we get x equal to 92. So 92 is our missing atomic number. The atomic number gives us the number of protons of that particle, and we use the periodic table to identify the unknown element as uranium. In this example, we're not given an equation to start with, so we have to take the information given and write the entire equation. Write the reaction for the positron emission of fluorine 18. First, we need to recognize that emission means that the positron will be acting as a product. This lets us know which side to write the positron particle on when we write the equation. We're looking at the emission from fluorine 18, so that will be our reactant. We can look up the atomic number of fluorine from the periodic table and find that it's 9. We know that one of our products will be a positron, which we use the symbol 01E, and we have an unknown product that we can determine the values for, because 18 equals 0 plus x, so we know that our mass number is 18. 9 equals 1 plus x for our atomic number, so we subtract 1 from both sides and we get x equal 8. When we look at the periodic table, we see that oxygen has the atomic number 8, so we know the identity of the particle. Nitrogen 14 is bombarded with an alpha particle to form a single product. Write the balanced nuclear equation. When we see bombarded, that tells us that the particle is going to be behaving as a reactant. So we know our alpha particle will be on the left side of our reaction. We know we're starting with nitrogen 14, and we can look on the periodic table to determine the atomic number is 7. We're going to add the alpha particle because we're going to bombard the nitrogen with that alpha particle, and we can determine what our single product is. We know that 14 plus 4 is equal to X, which is our mass number, and X will be equal to 18. For the atomic number, we know that 7 plus 2 will be equal to X, so X will be equal to 9. I can look at the periodic table and look at the atomic number of 9 and see that the identity of that particle is fluorine.